Aloha, Richard Halverson here. This is ITS388AL, and in the last video I showed you how to add code to your program so you can time the your your algorithms as they execute, your routines as they execute, and we showed you how you could compare both the the original bubble sort with the modified bubble sort. And so, and those routines were compared using arrays generated randomly with a random number generator. And in this video, I'm going to show you how to instead of using random arrays, we can compare our sort algorithms with a perfectly sorted array to begin with, an array that's already sorted. And then we can look at how it works with an array that's sorted in reverse order. So it's kind of like the worst case of sorting. So so if we look at the program that I had previously, I'm going to start with the program I had previously. And if we look at our binary, the main program here, we see that we had two arrays. And our fill array would fill up this array, fill up the first one here, and then we copied it from the first array to this array number 2 right here. So we had a copy of it. And then when we executed our programs, when we executed the original bubble sort like this, we executed it 100,000 times. We started the timer. And we executed the bubble sort array 100,000 times. Each time we copied the original array back into its original location. Because after we run the bubble sort, this array is going to be sorted, and we need to put back the original unsorted array to execute it again. And once that's done, we output the time that it took to execute. And then we went on to the second bubble sort algorithm, and we did the same thing, loading exactly the same array as we used for the first one, and we outputted the time for that one. All right, so what I'm going to do now is I'm going to show you how we can generate another, create an alternative to the fill array that will generate a perfectly sorted array to begin with. So let's create a new assembly language page here, a new item, and I'm going to name it sorted array .asm. And I think I'm going to start with copy array. That's maybe a little closer to what I'm going to do. Fill array. Yeah, I'm going to use copy array. So I'm just going to copy this whole thing. Control A, Control C, and go back to my sorted array and do Control V to paste. And I'm going to change all of the occurrences of copy to sorted. I just want to make sure I'm recording here. Recording, okay. So let's replace this, and this. And so this is going to sort, it's going to sort a destination array. I don't need, it's going to fill a destination array. Fill an array with ordered sequence of integer. And so we're going to start out by initializing the EDI with the destination array pointer. We're not going to need this. We're going to count that many times. We're going to load. We're going to start by moving into EAX value 1, start with 1. And we're not going to need to load anything in there. We store EAX into EDI. Then we need to increment EAX by 1 for the next time around. And then we need to increment EDI by 4, increment value store into next element. And this is going to increment by 1, and this is going to loop. It's going to do this. It's going to do this however many times count is, and then we should be done. This procedure uses EAX. It does not use ESI. It uses EDI. It uses ECX, and that is it. All right. So we've done sorted array. We need to also go over to the folder view and create a proto for it into Binary Search Inc. And the proto can look just like, well, heck, it can look like this one. Copy, paste. This is sorted array. And fill array with sorted integers. It's going to be a destination array. All right. Fill array with sorted integers, sorted array. Okay. So that takes care of that. Let's go back to this. And so let's try to run this. Let's build it. Oh, I got to go back to, okay, here we are at the, okay, build it. And succeeded. So let's put a breakpoint. This is the sorted array. Let's put a breakpoint just before we sort, just after we sort. And let's see, our test program 48. Okay. All right. Let's just see what this looks like. Debug. And this is our sorted array. And hit. And this is the bubble sort. Oh, never mind. Oh, I need to make sure we're using it. Hold on. I forgot to. Okay, we're in, it's in this program, and instead of calling fill array, we're going to call, instead of calling fill array, we are going to invoke a sorted array, ADDR array, array size. Okay, we want to run sorted array instead. Okay, so let's rebuild. Succeeded. Debug. Okay, we're at this breakpoint. So if we look at some memory, we are at, EDI is at 0, it's at 406000, or it's here, right here. So let's go to the next breakpoint, and it is filled up with numbers incrementing 09, A, B, C, D, E, F, 10, 11, all the way up to 30, which is 48 in decimal. Okay. And then we can continue this thing, and this thing pops up, and we see that the bubble sort, so the original bubble sort takes 585 milliseconds to sort this already sorted array, and the modified bubble sort only takes 41 milliseconds because it's just going to take one pass through and determine that the array is already sorted and it doesn't need to go any further. And of course, this still works. We can locate where's 38. It's in position 37. Okay. I'm going to do one more thing here, be fancy. I'm going to use this decimal adjust because that way, when we add 1, we can convert it back to something that looks like a decimal number. In other words, when we do a DAA, decimal adjust, that avoids that error message comes up because I'm running assembly language programs on my computer and the thing keeps thinking it's a virus. Decimal adjust, it can be uppercase or lowercase. And this is going to adjust, decimal adjust to skip integers with hexadecimal digits. And we can see what that looks like. So let's build this again. Succeeded, and now when we run it, it's gonna start it here, and then we continue, and we end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to 48. So you see it skipped all of the integers. Each time we added 1, we do this decimal adjust, and it ends up skipping. It corrects for skipping integers that have hexadecimal digits. So we don't see an A, B, C, D, E, or F. So it's kind of like we're counting in decimal here. So anyway, that's pretty cool. Okay, so so that's how we create this an array of sorted array. And now I want to create an unsorted array. So I'm going to just the opposite. So and how do I do this? I'm going to start with, I'll create add a new item, and I'm going to name it reverse sorted array. How's that? Reverse sorted array, and I'm going to start with sorted array here and copy that over to reverse sorted array. So with sorted array, I'm going to change this to reverse sorted. See what this does. Replace, 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 replace. All right. And this is going to fill an array with a reverse ordered sequence of integers. All right. So I'm going to start with EAX equals let's see, how can I do this? I'm gonna leave the counting the same, but I'm gonna EDX. I'm going to load. I'm gonna start at the top. So, and then I'm gonna decrement EDI each time. So here's EDI. Here's the count. I'm gonna add EC. Okay, so I'm gonna figure out what this is times 4. So shift left ECX comma 4, 4 bytes per word. No, it's shifted 2. Shifting it left twice is like multiplying it by 4. 4 bytes per word, and I think I need to decrement this. I'm not sure. Let's see, decrement ECX. I'm not sure. I could be off by 1 to adjust that, and then I need to add that to EDI, comma ECX, and then I gotta do this again because this is my loop counter. All right, so this set EDI to tail end of array. So I'm gonna write these digits in starting at the end, and so instead of I gotta subtract here, subtract 4 from EDI, and that's gonna decrement down to the beginning. So I wonder if this is gonna work. Okay, so I'm going to stop it here, and I'm going to stop it here. Let's go, and then I need to go to binary search test, and I have to change this to reverse sorted array. Reverse sorted array instead of sorted array. I'll leave this here, sorted array, and really I mean reverse sorted array. Just gonna run this one instead, and I need to go over to the file thing and add it to this. Sorted array, reverse sorted array, and reverse. That's all I need to do. And I got a reverse sorted array here, and I wonder if this will work. We'll see if it does. Let me build. Oh, I got to go back over to the other side, this one, and then build. And it succeeded. So let's debug this and see what happens. I turned off my firewall. I don't know why I'm still getting it. Okay, so this is the beginning, EAX, and EDX is equal to, oh shoot, I didn't mean to do that. Okay, I'm gonna move this one over. So it starts out, EDX is that. I don't know if that's right. Let's run this and see what happens. Boom. And I think we did it, yes. It goes from 1 to 48, and now EDI, it should be back, well, it's pointing to this location here, I guess. But anyway, so this is filled in correctly, it looks like. It's from here to here. And so then when we continue, we should get reverse order, and then we can hit any key. And the original bubble sort takes that long, and the modified one takes that long. The modified one takes longer. All right. I think the reason the modified one takes a little longer is because it actually does more work. Okay, there's going to be nothing saved. The thing we added to the modified bubble sort, which counts the number of exchanges in each pass, that's added work, and we aren't saving anything because we have to go through all the passes. And so if we look at the reverse sorted order, no, I'm sorry, not that. The binary search, where the binary search is. The bubble sorts. I keep saying binary. Bubble sorts. The bubble sort, the original bubble sort is, we just have an outer loop, and an inner loop. That's all it is. But with the modified bubble sort, we have this outer loop, but it actually does more work because we need to initialize EBX. We do that. And we need to count. When there's an exchange, we count the number of exchanges. That's more work. And then when we come down to this loop here, we actually do a comparison to see if there were any changes, and there will be changes. Each pass through the loop, there's going to be exchanges. So then it jumps back here. It skips this, it does the comparison, skips over this because it's not equal, and then it loops again. So you see, we actually add in the outer loop, we add one instruction and 2 instructions and 3 instructions. There's 3 instructions more, and there aren't very many instructions, so that adds a bit. And then in the inner loop, we have this right here where whenever there's an exchange, we add an instruction. So instead of 2 instructions to do the exchange, it's actually 3 instructions because we're counting. And so that is why for the worst case, this is a worst case scenario, the modified bubble sort actually takes longer than the original bubble sort. So so to recap what we have here, when we do the binary test, when we do the sorted, I'm going to take that out and comment the reverse sorted. So when we do the original sorted order, let's build this. And run it. When we do the original sort, if it's all sorted, then it takes 836 milliseconds to go through this and sort the sorted array. It's already sorted. But for the modified bubble sort, it's going to only take one pass through and realize that it's already sorted, and then it quits. So when we start out with a perfectly sorted array, it takes 1/20th. It takes, it takes half of 10% or 5% of the time with a sorted array. Without a sorted array, where we, instead of doing the sorted array, we do the reverse, the completely unsorted array, and build this. And we run this, we see that, that's right, I have these in there. We see that the original bubble sort, this is for a perfectly unsorted array. See, it's reverse order array. 842 versus 795. So it's this modified bubble sort is still a little bit faster, but slightly faster. That wasn't what we had before. Anyway, very close. Let's just try this again. Let me take these out of here, and let's run this again. Modified bubble sort is still a little bit faster. Okay, and if we do the if we actually do the random, which is this one, fill the random array. We don't use perfectly sorted. We don't use perfectly unsorted. We just use the random array. Build this one. This is going to be a little bit more realistic because random. We end up with there's a nice big array there, and the original takes 1178, and the modified takes a little bit less, 1064. All right, so that shows you how to create a perfectly sorted array and a perfectly unsorted array, so you can use those two to test your algorithms when you have, for the last assignment, assignment 9, when you're testing your additional sort routines. I recommend adding an insertion sort and adding a selection sort, because those are two pretty simple algorithms to implement. You're going to see, you know, there's the insertion sort is really fast when you already have a sorted array, and so on. You could, if you get ambitious, you can try to track down a quick sort or a merge sort or even a heap sort, and those are computationally less complex. The sort algorithms that we've been talking about, they require O of n squared computational complexity, whereas merge sort and heap sort and those sorts are O of n log n. So you will really only notice those with really, really large arrays, but they are faster. They're not stable, though. Stable means if you have two elements that are the same, and or two elements, if you have elements, if you have duplicate elements in your array, there's no guarantee that the order will stay the same with a merge sort, or merge sort maybe, but for not for other, no, for other for O of n log n sorts, the faster sorts. The faster sorts are not stable, but the slower O of n squared sorts, which is what we're talking about, they're simple. They're more simple. They're stable, but when you're running on really large data sets, you begin to notice that they're slower. All right, well, I hope this helps, and this should be it for preparing you for the last assignment. And in the last video, the next video I'm going to talk a little bit more. I'm going to help you out a little bit with some of the other sort algorithms. All right, thanks for watching.